All right, now which functions are not differentiable? Now that's the question. Which functions are not differentiable? So far we saw that if a function is discontinuous, then it's not differentiable. So first of all, discontinuous functions, i.e. Functions whose graphs have holes or breaks, right? Or let me say intuitively. So as you know, this is the intuitive description of discontinuous functions. In the exam, you have to verify with the definition of discontinuity or continuity, you know, and that if you want to show a function is discontinuous, you have to either show the limit does not exist or limit exists but is different from the value of f of a. But intuitively, functions with holes or breaks. So for example, this function or let's say, for example, this function. So these are discontinuous functions. So this is, let's say a, and this one here is a equals 0. Let's say this is a equals 1. So f of x at x equals 1 is discontinuous and therefore not differentiable, or here f of x again at x equals 0, again discontinuous and therefore not differentiable. So this is one type of function which is not differentiable. The other type, functions with sharp corners, functions whose graphs have sharp corners. So for example, you know, as we said, absolute value x at x equals 0. So it has a sharp corner like this, right? So in above, we verified that f of x equals absolute value x at x equals 0 is not differentiable, right? So we already verified this. And the other type of function, which is not differentiable, functions with vertical tangent lines. So again, please try to distinguish between the intuitive reason and formal reason. So we say, when we say, for example, functions whose graphs have sharp corners. Oh, I think the screen is freeze. Let me. Can stop share. And when we say the function whose graphs have sharp corners, that's the intuitive description. And in the exam, if you want to show a function is not differentiable, you cannot say because the graph has sharp corners. It's just an intuitive reason, and maybe gets let's say 1 or 2 points at most out of 10 points. But the formal reasoning for showing a function is not differentiable is with the limit, is with the definition of differentiability, which requires you to look at the limit of that fraction, you know, f of x minus f of a over x minus a. Look at that fraction and see whether that limit exists or no. If it exists, the function is differentiable. If it does not exist, the function is not differentiable. Yeah, so same thing here. So when so for sharp corners, so just in the exam, please remember that from the graph you can guess whether the function is differentiable or not, but for verification use the definition, use the limit. The third type of function, which is not differentiable function with vertical tangent lines. So for example, show that f of x equals square root of absolute value x is not differentiable at x equals 0. So how can we show that this is not differentiable at x equals 0? First, we can check continuity. If you remember, if the function is discontinuous, then we can immediately conclude that it's not differentiable. But if the function is continuous, then it may or may not be differentiable. So still we don't know. Okay, but the very first thing you can check is that whether the function is continuous or discontinuous. So note a limit f of x as x approaches to 0 from right is equal to limit root absolute value x approaches to 0 from right, which is limit root x approaches to 0 from right, and this is root 0, which is 0. And then the left limit similarly can be shown that is again 0, right? So then, here some people say, how come we have root minus x? Well, first of all, because absolute value x is minus x if x is negative. If x is less than 0, absolute value x is minus x. But still some people say, but shouldn't we have square root of a positive number always? And square root of negative numbers are undefined. So how come we have square root of minus x here? Well, the answer is minus x is not necessarily a negative number. It is possible that minus x becomes a positive number. If x itself is negative, then minus x becomes a positive number, right? So yes, we have a square root of minus x here, but x itself is negative, so minus x still positive. So that's okay. We still have square root of a positive number here, and the limit is 0. So we can say that the left limit is equal to the right limit equals 0. So that means the whole limit is 0. And which is same as f of 0. So that means the function is continuous at x equals 0. Now, if the function is continuous at x equals 0, so it seems the screen again is freezed. If the function is continuous, as we said, we cannot immediately conclude anything. The function may or may not be differentiable. So f of x may or may not be differentiable at x equals 0. We need to check. So how can we check? So limit f of x minus f of 0 over x minus 0, x approaches to 0. So this is limit root x minus root 0 over x approaches to 0. Now, if I calculate the root, it's root absolute value x, sorry, f of x is root absolute value x. Now, if x is bigger than 0, so then we have limit root x over x approaches to 0 from right. And this is limit 1 over root x, x approaches to 0 from right. And this is 1 over 0 plus, the answer is plus infinity. So the right limit is plus infinity. But this already implies that the whole limit does not exist, because if the right limit is plus infinity, you can, if you want, you can check the left limit too, but you don't have to, because this already shows that the right limit does not exist. And if the right limit does not exist, the whole limit does not exist either. So this part is optional. If you want, you can write it. If not, just to save time in the exam, you don't have to write it. So I can just immediately conclude that. Hence, the right limit f of x minus f of 0 over x minus 0 as x approaches to 0 from right does not exist. And this means the whole limit does not exist either. And that means f of x is not differentiable at x equals 0. Okay, so this is another example of a function which is continuous but not differentiable. So please remember, I gave this as an example of the type of function which has vertical tangent line. Now, why do we say that this has vertical tangent line? Because the right limit was infinity. Right limit of, not the function itself, the limit of function itself was 0, but right limit of this fraction, which is the slope of tangent line. So slope of tangent line from right is infinity. And if the slope of a line goes to infinity, means the line tends to be a vertical line, right? So slope of vertical line is undefined, but if the slope goes to infinity, means the line tends to become vertical. Right? So this one, if you look at the graph of the function, root x like this, looks like this, and root absolute value x looks like this. And as you can see, it has a vertical tangent line here. So x equals 0, vertical tangent line at x equals 0. Now see, when we say the right limit is plus infinity, means if you go a little bit towards right of 0, see the line becomes almost vertical, but with a positive slope. So like the slope could be 100 or 1000 and so on. Similarly, as you can see from the picture, if you go from a little bit to the left of 0, the tangent line looks like this. So the slope becomes like minus 100 or minus 1000, very close to be a vertical line, but with a negative slope, like minus 100, minus 1000, and so on. Okay. All right. All right, let's look at another example. Find the equation of tangent line at equation of tangent line at 2 y equals, let's say, x plus 2 over x minus 5 at x equals 1. So this question asks about equation of tangent line to a function at a specific point. Now, first we need to remind ourselves about the equation of the line. So recall equation of a line, or of the line with slope m passing through the point, let's say A and B, is given by y minus b equals m times x minus a, right? So this is what you learned in high school. If the line passes through the point A and B with slope m, the equation will be y minus b equals m times x minus a. Now here the line passes through through, so the x value is given as 1, and then y value is not given, but we know that if you have a point on the graph of a function, and if the x value is given, then the y value will be f of that x value. So f of x is given here, and x is 1. So then the y value will be f of 1, right? So this will be, the line passes through the point 1 and f of 1. Right, so see if you have, so here the equation, the graph would look like this. So this is x equals 5, and this is y equals 1. And at x equals 1 would be around here. So let's say, so this one, the graph should, at 0, it's a negative value. So at 0, it's negative. So like this. And then at 1, the y value will be how much? F of 1. And this is the tangent line that we are talking about here. So see, the tangent line passes through the point 1 and f of 1. So the tangent line passes through the point 1 and f of 1. How much is that going to be? If we do the calculation, so this is 1, and f of 1 means replace 1, x with 1 in the equation. So then I'll get 1 plus 2 over 1 minus 5. And then this is 1 and minus 3 over 4. Okay, and what about the slope? So to find the slope, we can use derivatives. We know that the slope m of tangent line at x equals 1 is equal to f prime of 1. And f prime of 1 means limit f of x minus f of 1 over x minus 1 as x approaches to 1. And then what is that going to be? This is limit f of x is x plus 2 over x minus 5 minus f of 1. F of 1 is minus 3 over 4 divided by x minus 1. X approaches to 1. And then this is limit x plus 2 over x minus 5 plus 3 over 4 over x minus 1. X approaches to 1. And then this is limit 4x plus 8 plus 3x minus 15 divided by x minus 5 times x minus 1, right? And then I'm getting common denominator. So there's also factor 4 here. So see 4 times x minus 1 is common denominator, then 4 times x plus 2 is 4x plus 8. 3 times x minus 5 is 3x minus 15, then divided by x minus 1. Right, so it's 4 times x minus 5 from here, divided by x minus 1. So 4 times x minus 5 times x minus 1. That's denominator, and numerator is 4x plus 8 plus 3x minus 15. X approaches to 1. And then this is limit 7x minus 7 divided by 4 times x minus 5 times x minus 1. X approaches to 1. Then this is limit. So if I replace x with 1, I get 0 over 0. Please remember, whenever you find the limit for derivatives, you always get 0 over 0. Because remember, what is the definition of derivative? Limit f of x minus f of a over x minus a, x approaches to a. So of course, if I replace x with a here, I get f of a minus f of a over a minus a. So I'll get 0 over 0. So whenever you calculate derivatives, you get 0 over 0, which means you have to simplify. So how do you simplify? Well, we already saw in the previous chapter how to simplify the limits of the form 0 over 0. For example, if there are polynomial over another polynomial, you have to factorize, and so on for other type of functions. So here we will have limit. So I can take 7 out. So 7 times x minus 1 divided by 4 times x minus 5 times x minus 1. X approaches to 1. Now x minus 1 cancels with x minus 1. And then I'll be left with 7 over 4 times x minus 5. X approaches to 1. So that's 7 over 4 times 1 minus 5. That's minus 7 over 16. So this is the slope. So slope is minus 7 over 16. And the point we said is 1 and minus 3 over 4. So the equation of the line will be, of the tangent line, will be y minus 3 over 4 equals minus 7 over 16 times x minus 1, or y equals minus 7 over 16x plus 7 over 16 minus 3 over 4. So y equals minus 7 over 16x. And then 7 minus 12 is minus 5 over 16. Okay. Now let's look at another example. So this one, the example is with graphs. So remember, most of the question, the exams and exercises are either using formulas or graphs. So most of the time, students are more comfortable using formulas, but you should also know how to deal with graphs as well. So let's look at this graph question. So it says match the graphs of the functions as shown in parts A to F with the graphs of their derivatives derivatives in parts capital A to capital F. So we have to match the graph of function with their derivatives. There are 6 graphs for the function, 6 graphs for the derivatives, and we have to find out which graph corresponds to which derivative graph. So part A here, there is a function which looks like this. So these are for the original functions. And then after this, I will sketch the graph of derivative functions. So right now, original functions. And then the next graph looks like this. This is part B. And then there is part C here. And then part D. And part E. And then finally part F. Okay, so these are for the functions. So let me write here, functions, original functions. And now derivative functions. Derivative function. So for the first function looks like this. And second function. And then there is a third function. Fourth function. And fifth function looks like this. And finally, the last function and sixth derivative function looks like this. Okay. All right, let's start with the first original function. It's a very simple function. It's a piecewise function. The one in part A is piecewise function, and it has 2 pieces. The first piece, so let me show you the cursor. The first piece from here to here. So when you want to find the derivative of a function, please, the only thing you have to remember is that derivative of a function at a point is the slope of tangent line at that point. So derivative at these points. So what are the slope of tangent lines at these points? Well, this is the graph itself is a straight line. So the tangent line is the line itself. So for example, at this point here, the tangent line is same as the original line here, or here again, tangent line is same as original line, because the graph is a straight line itself, right? So at all these points, the tangent line is this line itself. So what is the slope of tangent line? The slope of tangent line will be slope of this line. And how much is the slope of this line? So this is a line with a positive slope, and a line with a positive slope and constant positive slope, right? Because the line is not changing, so the slope is not changing either, right? So the derivative of this function, which is slope of tangent line, which is slope of this line, which is a constant, positive constant. So up to this x value, the derivative function must be a positive constant. So let's look at the derivative functions that we have here. Well, this is not a, so up to this point, we established that from minus infinity up to this point, we need to have a function which always takes a positive constant, same positive constant for all values from minus infinity to some x value around here. But this is, of course, not a constant function, not a positive constant function. This one, not positive constant either. This one is not a positive constant either. But this one, see, this one is a positive constant, could be, for example, 1 or 1.5, something like that. So positive constant from minus infinity to this x value, as we said, it's a positive constant, this constant here, positive constant. After this point, the line becomes a horizontal line. And the tangent line still, because it's just one straight line from this point to infinity. Again, because the graph is a line itself, the tangent line is same as the original line. And the slope of tangent line, which represents the derivative, will be slope of this line. Slope of this line, this is a slope of a horizontal line. Slope of a horizontal line is 0. So from here to infinity, the slope of tangent line is slope of this line, which is 0. So the function must take the value of 0 from this point to infinity. So constant function 0 from this point to infinity. Again, consistent with this graph, from this point to infinity, constant function 0. So let me say solution. The graph in A matches with graph in D. So I can explain it this way, that let's call this one x1, and let's call this one x1. So for x belongs to minus infinity to x1, the graph is a straight line with a positive slope. With a positive slope, so the tangent line, so the slope of tangent line on minus infinity to x1 is a positive slope. Again, is a positive slope. It's a positive constant. Consistent with f. Similarly, on x1 to infinity, the tangent line is a horizontal line which has the slope of 0. So derivative function because derivative function means slope of tangent, and derivative at any point is slope of tangent line at that point. So derivative function equals 0 on x1 to infinity. Again, consistent with what we have in F. And finally, note that at x equals x1, the function is not differentiable, right? Because the left limit, left tangent line, the slope of left tangent line not same as right tangent line. So left limit of f of x minus f of a over x minus a is not same as right limit f of x minus f of a over x minus a, which means that limit does not exist graphically because left tangent line is not same as right tangent line. So the function is not differentiable, which means derivative function is undefined at x equals x1. So, and that's why we have two holes appeared in the graph of capital F at x equals x1. Right? So you may wonder why we have two holes here. Oh, sorry, I meant D, this graph. Oh, yeah, here I wrote D. Here, by mistake, I said F, I meant D. And also here, I meant D. Here, I meant D. Okay, so here you may wonder, why do we have holes here and here? Not even one of them is filled. Because the function, the derivative function at x equals x1 is undefined. Why? Because the slope of tangent line at x equals x1, at x equals x1, slope of tangent line is undefined. The left tangent line is this, which has a positive slope. Right tangent line is this, which has a zero slope. So the tangent line here is undefined. So derivative here is undefined. So derivative function is undefined, which means that we need to have holes here and here, both of them. Because if we fill even one of them, then the derivative function will be defined at x equals x1. For example, let's say if this is 1, if I fill it here, then that means derivative at x equals x1 is 1. But that's not supposed to be the case. At x equals x1, the derivative is undefined. So it must have no values. And therefore, we need to have two holes here. Okay, so this is for the first part A. And I wrote the explanation too. B is similar. You can try to do B yourself. Let me do D. So B exercise. And let me do, sorry, C. I can do C or D. Let's do C. So C matches with what? So first of all, again, the only thing you have to remember is that at any point, slope of tangent line at that point gives you the derivative at that point, derivative function at that point. So for example, at x equals 0, what is the slope of tangent line? At x equals 0, this is the tangent line, which has, let's say, m1, I can call it m1, has the slope 0. At, let's say, another point, let's say, for example, here, x equals a. What is the tangent line? The tangent line looks like this. And then this is, let's say, m2, which has positive slope. But as x goes towards infinity, still slope is positive, but becomes more and more horizontal. For example, see here, the slope is still positive, but becomes very close to become horizontal. Horizontal line means slope close to zero. So the slope becomes closer and closer to zero. Same thing here. So see M1, and on the other side, again here, similar, not the same thing, but here, M2, or I can call it M4, for example. M4 is negative, but if I move farther away, for example, let's say this one, M5, still negative, but becomes closer and closer to become a horizontal line. So M4 negative, M5 negative, but M5 is closer to become a horizontal line compared to M4. So M5 becomes closer and closer to zero. So we are looking for derivative function which represents the slope. Must be a function which, first of all, takes zero at zero, takes zero because the slope of tangent line is zero. Left side, it must have positive values because slope is positive. Right side must have negative values because slope is negative. So let's look at the functions. So this one at zero is not zero, not good. This one at zero is zero. On the left side, positive slope, positive values. On the right side, negative values. And as x approaches towards minus infinity, like we said, the slope becomes closer and closer to zero because the line becomes closer and closer to become horizontal. And also from the other side at infinity, as x gets larger and larger, the line becomes closer and closer again to become horizontal. So the slope becomes closer and closer to zero, which is the case here. So this graph has all the conditions that we need, but again, the others won't have it. So for example, here at zero is not zero. This one at zero is zero, but it doesn't have the other features that you want. For example, on the right side, it must have negative values, but here it's always zero, remains zero on the right side of x-axis. This one, yes, at zero, it's zero, and left side positive, right side negative, but it doesn't have the feature that I said that as x goes to infinity, the y values, the slope must get closer and closer to zero. But this one as x goes to infinity, the function is not even defined. There is no graph here, right? Or here, so the function is not even defined. So can't be this one either. And this one, again, obviously doesn't have the features that we want. Remember, we said that on the positive side of x-axis, the derivative function must have negative values, but this is not the case. Sometimes positive, sometimes negative, sometimes positive, sometimes negative. So obviously this is not the case either. This is not acceptable either. So we can say that part C matches with the graph given in capital B. So how can I justify? Just write down what I said here about the slope of tangent lines, and just mention that the derivative function at any point is the slope of tangent line at that point. And the graph in B has has all the features that we want. So let's say express a justification. So again, at x equals 0, we have horizontal tangent line. So that means f prime of 0 is 0. Again, this is consistent with B. See, f prime of x is a function, right? So if the value of a function at 0 is 0, means that function must pass through origin. And in B, the function passes through origin. If x is less than 0, then the slope of tangent line is positive, and it approaches to 0 as x approaches to minus infinity, since the line become more and more horizontal as x approaches to minus infinity. So what do we need? So we can say that f prime of x is less than 0, is bigger than 0, is bigger than 0 for x less than 0, and limit f prime of x is 0 as x approaches to minus infinity, i.e. y equals 0 is a horizontal asymptote for f prime of x. Like I said, f prime of x is a function itself. If you know that a function is bigger than 0 for x less than 0, means what? Means that the function must be above x-axis, right? When you say a function is positive, the output is positive, means it's above x-axis. Above x-axis, for which x values? When x is less than 0. For this part of x-axis, the function must be above x-axis. And as x approaches to minus infinity, means gets farther and farther from negative side, the y values of this derivative function must get closer and closer to 0. So in other words, the limit of this function must be 0 as x approaches to minus infinity. If the limit of a function is equal to 0 as x approaches to minus infinity or infinity, in that case, we said that we call y equals 0. We say that y equals 0 is a horizontal asymptote for your function. Remember the definition of horizontal asymptote. We said y equals a is a horizontal asymptote for, let's say, g of x, if limit g of x is a as x approaches to infinity or as x approaches to minus infinity. So y equals 0, which means the x-axis must be a horizontal asymptote for your function. And again, it's consistent with B. Y equals 0 or x-axis is a horizontal asymptote for your function, for this function given in B. So let me say again, consistent with B. Both consistent with B. Similarly, if x is positive, the slope of tangent line. The slope of tangent line is negative. And what else? So slope of tangent line is negative, and as x approaches to infinity, the slope becomes closer and closer to 0. So what can we conclude? We can say that f prime of x is negative for x bigger than 0, and limit f prime of x as x approaches to infinity is equal to 0, again, which means horizontal, which again means y equals 0 is a horizontal asymptote for y equals f of x. Again, both these conditions, both of these conditions are consistent with the graph in B. So the graph in B has the feature that, so you want the function, the derivative function, to be less than 0. Less than 0 means below x-axis. below x-axis if x is positive. If x is positive, means if you're on this side of x-axis, your function is below x-axis. And as x approaches to infinity, the y values of derivative function become closer and closer to 0, which means this y equals 0 is a horizontal asymptote for your function. Okay, and all these features given in a graph in B, but other graphs do not have any of these conditions, or at least some of these conditions are not valid for the other graphs. Okay, so I matched the graphs given in A and C with the graphs of derivative functions, and I wrote the reasons. So the other parts are also similar, so you can do them as practice. So other parts, so B I already left as exercise, C I did it for you. So parts D and E and F, so these are also exercise. Okay, so please try to match these graphs also with the graphs of derivative functions, and also please make sure to write the explanations that why do you think this original graph matches with this, for example, derivative graph. Write down the explanation like I wrote here. Okay, guys, so thank you. And so next time we will have the exam, and then we'll continue this topic of the differentiation next week. Okay, so thank you, and see you.